Things off, I wanted to present a few slides and kind of give some background on the topic. Our focus is on open source CPUs, but I think the main open source today is RISC-V, so that is going to be the main focus of the discussion. So I understand not everyone here is a CPU designer, so I did want to have a little bit of background here. So if you know what a CPU is, forgive me, but I did want to remind people that the CPU is the thing that executes the software in a processor, and so that CPU determines what kind of software you can run. CPU has a particular instruction set, and so if your software is compatible with that instruction set, then it will run on that CPU, and if it isn't, it probably won't. So the most popular instruction sets, which you've probably heard about today, are ARM, which is in pretty much every smartphone, as well as in a lot of automotive processors, a lot of consumer goods. And then Intel has the X86 architecture, which appears in almost every PC, in server processors, in some other equipment. The X86 architecture is basically a closed architecture in the sense that only Intel and AMD can produce processors using that architecture. ARM, on the other hand, is a little bit different in that ARM licenses its instruction set and its CPUs to other companies who can then use it to build their own chips. So the ecosystem works a little bit differently. So this gives you an idea of kind of how popular these instruction sets are by unit volume. ARM is by far the leader. More than 20 billion chips last year used an ARM CPU. And then there are several other kinds of CPUs that are available today. A lot of these are licensed from companies like MIPS, and ARC is from Synopsys. Cadence has Extensa. So, and then X86, as I said, is not licensed, and the volume is pretty low, if you can even see it on the graph here. But because of the high dollar value, X86 actually generates the most revenue, which is why people hear about it. So RISC-V now is coming to the party. It's a pretty new instruction set, and really bringing a different and disruptive business model. It is a complete instruction set for building CPUs that anyone can use without a license, without paying license fees, and anyone can modify it, add their own instructions, and create something customized for their own application. So this is different from ARM's model, in which you have to get a license and you have to pay for it. And you can also get open source CPUs. Again, you just download from GitHub, get the code for the CPU, and use that to build a CPU into your processor. Now, this is not the first time we've had an open source instruction set. There have been some other attempts in the past, but this is the first open source instruction set that's really gotten a lot of traction. So, we see a lot of companies very interested in RISC-V. Some of them are established CPU IP vendors, like ARM and Krste, that have decided to adopt the RISC-V instruction set. There's new companies like SiFive that have started simply to focus on RISC-V. We see big established companies like AMD and NVIDIA that are using RISC-V not for their main processor, but for some of the smaller processors inside their chips. And then Western Digital has committed to switching all of their products over to RISC-V over the next few years, and that could total over 1 billion cores per year. And 1 billion is a big number, but if you recall from the previous chart, that would be a couple % of the overall CPU market in and of itself. So that would be a good start. And then we also see a lot of smaller companies attracted to Risc-V so that they can customize it and build innovative products. So there are some drawbacks still today to using Risc-V. Compared to established instruction sets like ARM and X86, the amount of software and hardware tools are more limited. The number of operating systems that run on Risc-V is also more limited. We don't have Android, we don't have Windows, some of the popular operating systems like that. The open source cores that are available today are pretty low performance, so they're only good for some of the, some lower end tasks, not so much for smartphones or PCs yet. And then some of these open source CPUs don't have all the same features that a commercial design would have, particularly things like manufacturability and testability may not be baked into some of these CPUs. So you can get a licensed CPU from companies like SiFive that will have all of these commercial features baked in, but then it does cost money. It's not free anymore. So I'm sure we'll hear more from some of the other panelists about how they're working to change some of these things over time, and I think we will see a lot of innovation and improvement in Risc-V. But today it still has some of these drawbacks. And the last point I want to make is there's a lot of talk about the license fees and how much you can save through that. So this chart shows kind of how much it costs to design a high-end SoC, and this is a very complicated one that has lots of cores, and a lot of the cost that goes into the chip design is the physical design, and then all of the verification that has to be done, and then the tape-out cost, which is a one-time upfront cost, can be $10 million in a leading-edge process. So companies spend a lot of money to try to make sure everything works right. And then typically, a chip company has to develop a lot of software to go along, with their hardware. So there's probably, roughly half of the spending is on software. And so the two boxes at the very bottom are really where you're designing the CPU as well as all of the other components on the chip. And so about 15% of the total cost is this design. And then of that 15%, some small piece, maybe 1 or 2% of the total is the CPU. So, when people are talking about how much you can save, it's a fairly small percentage of a highly complex chip design, that you might see in a smartphone or a PC. And so, whether you want to risk your design on an open source CPU is a tough decision for some of these big companies. I think for smaller companies doing smaller projects, it makes more sense. So, with that, I want to go ahead and start introducing the rest of the panel. These are some of the topics and questions that we'll be talking about tonight, and try to understand, where Risc-V is going, and how it's going to change over time. And most importantly, how can you monetize what's going on with this open source architecture? So with that, I'd like to quickly introduce our panel. Let's see, there we go. So we do have one panelist here virtually, and that's Kauchik Roy, who is the Senior Director of Western Digital Capital. Kauchik, are you on the line?
Yes, can you hear me?
Yes, very good. So could you take a moment to tell everyone what you do at Western Digital, what your background is?
Yeah, my background is mostly on the financial services. Most of my life I was a sell-side security analyst covering IT infrastructure companies. I've been on the buy side as well, and a few years on the venture side. And now involved with corporate development and strategy, and more specifically on the Western Digital Capital side.
Great, thanks. And at the far end here is John Heinlein, who is the Chief of Staff to the CEO at ARM. John, can you introduce yourself?
Hi, I think I'm the home crowd here. I have a PhD from Stanford in computer architecture, so I'm very excited about that. ARM, I've been at ARM 10 years doing a lot of different functions in some of our business units, in some of our outbound marketing strategy, and most recently with the Office of the CEO. But I've long followed this area, and it's an important area for me and for us. And we'll talk more about ARM later on. Great,
great. And next to John is Art Swift. Art is VP of Marketing at Esperanto, which is a company that is using RISC-V in their processor. Art, can you tell us a little more about yourself?
Sure. First, Esperanto is probably the biggest stealth company you've never heard of. We have approximately 100 engineers now. We've quietly raised tens of millions of dollars. Western Digital is our only announced investor to date, but they're just a small piece of several. And we're building energy-efficient machine learning accelerators based on RISC-V. So basically, thousands of RISC-V cores on one device. Personally, I began my career as an engineer working on chips for the Cray computers. And then I've had the pleasure of launching some of the most important RISC processors in history, the Alpha for digital, UltraSpark for Sun. I worked with John at Transmeta launching the Fission X86 processors, consulted for Intel, and I've been one of ARM's biggest customers at one point in my past life. So I've been around the block in the processor wars. So I have a few comments from both RISC-V and a proprietary processor point of view.
Great, thanks, Art. And finally, we're pleased to have Krste Asanovic, who is the co-founder of SiFive and one of the inventors of the RISC-V technology. Krste, can you tell us a little bit more about yourself?
Yeah, so it's great to be here down at the Stanford Faculty Club. I'm actually faculty at UC Berkeley. I don't get to, you have much nicer digs here than we do. Public school, so I'm a professor at Berkeley. RISC-V came out of my research group at UC Berkeley. Today I'll hopefully get a chance to talk about SiFive. I spend a lot of my time talking about RISC-V. It'd be good today to talk about building a company around RISC-V today.
Great, and speaking of which, I believe you have some slides to share with us, so
okay.
You may have the clicker.
All right, so like I say, it's fun to talk about SiFive instead of RISC-V. So why did we want to do a company? And how do you build a company around a free and open ISA? So hopefully something will come up. So our real goal is we love building chips. And we feel like Silicon Valley, there's not enough chips going on. The silicon has left Silicon Valley. What happened to the hardware, right? And it's a great time right now. Unfortunately, I've used this slide many times, but I feel this trivializes the problems right now in North Carolina. I'm sorry. But there is a perfect storm happening right now in the semiconductor industry. So storms happen when hot air meets cold air. Hot air from the equator, cold air from the north. The hot air is all these new apps need all this compute. AI, IoT, they need it in different forms. The markets are getting very fragmented. There's an incredible demand for custom silicon. The cold air, as Linley pointed out, it's really hard to make chips these days. It's very expensive. And the other thing is we've ended scaling. So standard parts are not scaling. The old model was build standard parts, program them, wait for the next generation. That doesn't work anymore. That's what people want custom silicon. So if you look in the industry, we've changed from a horizontal business model to vertical models. Apple builds their own chips. Why? They don't sell chips, they sell phones. Google builds their own TPU engines. Why do they do that? It's because they don't sell the chips, they sell the service. Tesla is building chips for their cars. Why is that? They don't sell the chips, they sell the cars. So these big companies have realized that their products are better when they can customize the silicon to make their products look better. So this is a new vertical model appearing in the semiconductor industry. Now, what about the little guys? Where are the startups doing all this stuff, right? Well, if you look in the software side, there's plenty of examples. Instagram, 13 employees, $1 billion valuation. Have you ever seen a hardware company with 13 employees and $1 billion valuation? No. Why doesn't that happen, right? Well, there's too many experts needed. You want to build a chip, there's all this expertise. Building the CPU, soft core, that's the easy part. Doing everything else is really difficult. Linley alluded to this in the block diagram. There's the breakdown. There's all these skill sets you need to put a chip together. And you can't do that easily doing a startup. Okay, so this is the software view of the world. I have a little piece of IP. I have this idea about sharing photos with my friends. I go take all this open source software, slap it together, build a quick prototype. I can scale it to millions because Amazon is there to scale a data center out. What do you have in the hardware industry? You don't have anything like that right now, right? But what we're trying to do is change this. So the new model is, you have a great idea for your little bit of IP. We want to help you provide all the other stuff you need. Some of it will be open source, some of it won't be. But then you actually get the chips out there, make them made, get in production. So what SiFive is really doing is building this stack, and we're providing what we call SiFive Silicon Cloud Services. We want to make it easy for, two guys, two gals in a garage to come up with an idea and build a whole chip company, right? Without needing a huge amount of investment. That's the goal of SiFive, right? That's what we're doing. So we're building this silicon in the cloud model where we'll provide everything you need. You'll come to our website with your idea. We'll take care of everything else. We'll provide the cores, the other IP. We'll work with partners to give you other IP. We will assemble the chips for you. We'll go to manufacturing, do production, logistics. We can scale up to hundreds of millions of chips shipped if you actually reach the market. Right? This is what we're trying to do, is put this all in the cloud. You don't have to go build all this yourself. There's no reason to do that anymore to build a chip company. So what are our actual products right now? There's 3 basic product lines in the company. So we have, you can come to our website. This is being set up. You can come, we'll sell you soft cores. You want a traditional soft core IP. If you're building your own chip, we can give you configured RISC-V cores that are verified, guaranteed. We stand behind them. We offer all the features. That's one product. Second product is we can build bigger subsystems, multiple cores wired together with some other IP. We'll again give you the soft RTL. But I think what's most interesting here, we can take all that, put it on the silicon, and give you prototype very, very cheaply. Our goal is to get you prototype about 1/10 of what it costs you right now to get to prototype silicon. And that will, I think, open the floodgates of innovation. Now, lots of people can afford to get to prototype silicon very quickly. Once you're done, our goal of doing this is we hope to have more at-bats, so we get more home runs. Anyone that goes to volume, we make money by selling lots of chips in production. So we make the chips for you, we print your label on the chip, we sell you the chips, you sell them on, we make money from the chips, and we share the profits with our IP partners. That's the basic business model at SiFive, okay? So behind the scenes, what's our secret sauce? We're building this stack to automate chip production. We've taken chip design. This is other ideas from Berkeley. RISC-V was one thing we did at Berkeley. People are less aware of the other stuff we did on agile hardware development. So we're automating a lot of the processes in chip design. Our goal is actually get to the point where 0 SiFive engineers are involved in making your chip, right? We want it to be as automated as possible. Starting from simple chips, over time we'll move to more complex chips, but that should be true. So a lot of compute time, but very little human time in getting that chip finished. That's our goal at SiFive, right? So here's a quick screenshot of our core designer, which is just, simple web interface. This is how you build chips in the future. You don't sit there banging out tickle scripts, right? That's not how you do stuff, right? We want to make it really, really easy. And our goal is not to sell to chip makers. We want to sell to product developers. You have an idea for a product? We want to make it easy for you to build a chip for your product, right? So we're selling to product makers, not chip builders, right? That's our end goal, is to get to that point. So now, to build a chip, a core is only one tiny piece of the story. You need all the other IP. You need all the PHYs, the DDR PHYs, the PCIe PHYs, all this other stuff. That's really exotic, expensive stuff. And that's often a big barrier to doing your first chip, getting those things licensed. We have this design share program. We have many people signed up. Third party will pre-arrange with us to have their IP available on our platform. You don't have to negotiate with 100 different IP vendors. You don't have to figure out how to integrate all those pieces. We do all that work ahead of time. So you can just come in, use the IP, put on your chip. We make the chip for you. We've done the deals. And the reason the IP vendors like this, they don't have to talk to 1,000 customers. They just talk to us. Also, the IP stays on our servers. It doesn't get sent out to 1,000 customers. Dealing with big markets like China, for example, this is a big concern for people. So our model is you bring the IP to us, we then resell it to the bigger community. You don't have to deal with these people. You get this channel that lets you sell your IP. Not just big IP vendors, but small mom and pop shops. You have some IP idea. We can give you a channel now to get to many, many customers in this big market. All right. So SiFive, we're actually a lot bigger than people realize. We have over 300 employees now, 12 offices around the world. I recently acquired Open Silicon. A lot of this expansion came from. Ready, shipped, a lot of experience. The team has shipped over 300 tape outs, hundreds of millions of SoCs, very low DPPM. We have design teams everywhere, and we're growing very, very rapidly. Market. So Arun asked me to talk about market. So if you look at traditional custom SoCs where people would not just use a standard part off the shelf, but build something for their product, it's been about 5 billion a year or so, whereas the whole SoC market is 100+ billion. Our goal is to convert some of that 100+ billion into custom SoCs. So our goal is not just the current custom SoC market, but convert more of that standard part SoC. Some people hear from Xilinx, but that's a standard part right now. We'd like to turn those into custom SoCs, a lot of those parts. Okay, so we talk about open source. Why open hardware? Why does this help? Well, RISC-V helps. It means that we can build our own cores. We don't have to talk to people. We can build our own cores. It's not just about license cost. It's about flexibility. We can add stuff. We can change them. We can build different varieties of cores. It's not just the cores. There's the interconnect. There's a free and open interconnect we use called TileLink. We also been open sourcing more of the CAD tools. This helps reduce the cost of doing all this. Providing emulation, using FPGAs in the cloud to do emulation to lower the cost again of doing development. And the big thing about open sourcing all the interfaces, everything, we want our customers to support themselves. It's a win-win. It's cheaper for us than supporting them behind a proprietary barrier. It also empowers the customer to go do stuff. We've had customers build their own stuff on our platform, do everything, get the prototype up and running, then come to us to convert it to silicon. And that's ideal. We don't have to support them. We give them everything they need. They can develop by themselves without our support. So little prediction, I did this at Linley's conference a couple years ago. I'll repeat the prediction. Eventually, open source CPUs will be the best CPUs. What do I mean by best? They'll be the ones that people choose to put into production, right? It's not going to happen right away. It'll take a little bit of time. The thing to realize, is this possible? Well, CPU designs, if you do them in Chisel, are tens of thousands of lines of code at most. Do them in Verilog, maybe it's another factor of 10. The community is going to build this verification collateral. CPUs are not moving that fast. There's not that much innovation in CPU design. And my message to everybody is CPU design is not a long-term defensible IP strategy for anybody. It's going to, near term it's okay. You'll make some money in the next few years, but 5, 10 years out, it's not going to be a defensible place to be. It's just too easy and simple. I teach classes, other people teach classes, people build stuff. Once it's open source, people can build on each other's work. And so this is not going to be long-term defensible. I've looked at a lot of AI engines. It looks a lot like stuff I saw in the 60s, 70s, 80s, just rehashed. That's not defensible either. But every chip needs verified cores. You need to do some work. Okay, done.
Perfect.
All right.
Told you I'd make it in time.
All right, great. Thanks, Krste. So I'd like to get the discussion going. So Art, can you tell us more about why Esperanto chose RISC-V and as much as you can, kind of what it is that you guys are doing that's interesting with it?
Sure, absolutely. So Esperanto is about 4 years old now. We just passed our 4-year anniversary. And we were founded by a guy named Dave Ditzel, who's one of the progenitors of RISC processing, who wrote with Professor Dave Patterson the original Case for RISC paper. He's quite an instruction set authority. He's an expert in binary translation. And he assembled a really great team at Esperanto very early on, before we had raised any money. And we actually were thinking about developing our own instruction set. And we did a shootout of existing instruction sets, ARM versus RISC-V, and what we could do. And son of a gun, if those RISC-V guys hadn't done a pretty darn good job. The efficiency of the instruction set was virtually as good as ARM, but much less complex. So in other words, we could use less gates to implement a processor, which meant for our purposes, a smaller processor uses fewer gates, less transistors, which means inherently lower power, which means we could focus on energy efficiency. And for our purposes, machine learning in a data center or machine learning at the edge has extreme energy use constraints and thermal constraints. So RISC-V was the perfect vehicle for us. So we shot our own plans to do our own instruction set. We embraced RISC-V, and for us, it's been a fantastic choice. When we did the comparisons versus a competitive ARM core, had we been able to get one, and we might talk about that later, it was much smaller. It was, in terms of gate count and complexity and simplicity, it was just much more elegant, and we had tremendous die size and energy savings. So that's basically why we embraced RISC-V.
Great, great. Thanks for sharing that. John, I guess you can maybe give us the counter view, but what is it that ARM delivers that RISC-V doesn't? I mean, why should someone pay a license fee to get an ARM core?
Sure. So I think if you look at Krste's point, actually I think we fundamentally agree with the point that customizing your chip is important. And actually ARM's entire business model is built around the idea of customizing chips. We just disagree at what level you customize. Because for the vast majority of applications, and there may be some for extremely specialty applications where you really want to get deep in the weeds, but for the vast majority of applications, there's a lot of customization that can be gained at other levels, including the myriad cores we offer. I think we've made, if my count is right, 120 cores and GPUs over our lifetime, which spans an incredible range from ultra low power to ultra high performance. So there's a lot of choice you have from the first point. Then how do you configure that? What are the configurations themselves? What system environment do you put around it? What peripherals do you put around it? So fundamentally, we agree that you want to customize your core, and our partners do. In fact, the thing about ARM that differentiates us, as Linley mentioned earlier, from say Intel, which is ultimately a chip company that sells chips, is that we really talk about our customers as partners. If you meet anybody from ARM, they're going to keep saying, ARM partners. What is this ARM partner thing? It's because ultimately we want to make our partners successful. We provide our IP, and there's a lot of value that comes along with that. But our partners have to put it in their chip and ultimately ship it for us to get the second half of our revenue, which is royalties. And we do everything we can to make them successful. And we can go into a lot of technical details, but ultimately we believe in this configuration and we offer it. But what we offer then along the way is proven cores that are verified, that are solid, that we stand behind, and that also have compatible specifications. So when you write code on these cores, it's compatible with other cores, which allows you to leverage a huge amount of software ecosystem and installed base. And that's been incredibly valuable for our partners.
Great, thanks, John. And Kaushik, can you give us some perspective as an investor as to what you see with RISC-V and how that can be a profitable area?
Yeah, our goal is to seed the ecosystem, the RISC-V ecosystem. And all of you mentioned the benefits of RISC-V. And what we saw is that there wasn't, and Krste I think mentioned it, that there wasn't a lot of innovation in the processor technology. If you look at other areas, for example, storage, like data storage, in the last decade or two, there were like 250 startups. If you look at networking, there were many startups, if not 250, but then there were many. But if you look at the processor technology, there are only a handful of processor-related startups. So there was a lack of innovation. And then the third thing is that there are new applications now. There's a need for special purpose, customization, and all these things you mentioned, that there's a market need for something like this. So, and that's the reason we decided to seed the RISC-V ecosystem. And it's not just for the benefit of the industry, and I think you mentioned that our CTO has said, we're going to bring out in-house the controller technology and use RISC-V. So we benefit as well. At the same time, we want the industry to benefit as well.
Great, thanks. So, I mentioned, in my introduction that most of the open source cores available today target, more lower cost, lower performance points. So, I guess first of all, Krste, would you agree with that? And if so, what kinds of applications are those cores getting used in?
No, that's certainly true. Like most of the open source cores are reasonably traditional, like 3 to 5 stage in order single issue pipelines. There is, like from my group in Berkeley, we did do an out of order core. That still needs a lot of work. It's not a commercial class core yet, but it's a starting point. I think the low end embedded cores, I realize there's a lot of cores, most of those cores you talked about fall in that category. And I think most of those products would be okay with one of those cores. It does need, I agree with John, you need commercial support, verification of these things to be sure if you're going to put in an expensive chip. But they're close to what you need. I think to realize you will need to invest more to make sure it really works. But they are similar in capability to the commercial cores, those open source cores. And over time, like I said, I think it's going to take a little bit of time. They will become actually usable as commercial cores. The high end will take longer, but that will also come down. I think the thing is, once you can open source the core, the thing is, it enables to have the free and open spec, means you can open source, which means the community can work on it together. And that's really hasn't really been there that much in the past, and that's the different thing. And it will take some time, but I think the open source cores will get a lot better over time.
Mm-hmm.
Yeah, and cover more of the application areas. The thing with RISC-V really is we designed it, the research project it came from was all about building specialized processors. So, general purpose processing is kind of relatively boring. There's not that much innovation, but there's a lot of extensions and specialization. That's really what RISC-V was designed to do, is to support those exotic different things you build around the base core.
Mm-hmm. So John, would you agree that most of the ARM core shipping today are in these kind of lower cost areas?
Well, if you look numerically, you showed this 21 billion units, and we're at 125 billion with the B units cumulative over the 27 years of ARM. Numerically, around, I think it's 50 or 60% of last year's shipments were in what we call Cortex-M. We have three families: Cortex-M for microcontroller, Cortex-R for real-time, things like a read channel, hard disk, or safety-critical applications, and Cortex-A, which is the app processor, which is the one you probably know and love in your smartphones and so on. So if you look at that, around 60%, if I have to recall correctly, of last year was Cortex-M, and that ranges all the way from Cortex-M0 Plus, which is extremely simple core designed to run like a coin cell battery for many years in an embedded application, all the way up to our more recent Cortex-M7 and cores, and more recently even higher end, that provide much more advanced processing, DSP and things like that. So that whole spectrum spans quite a broad range. And we want to make sure that's very approachable for everyone. As a matter of fact, earlier this year, I think it was last year, we actually made our two most popular cores, numerically most popular, Cortex-M0 Plus and Cortex-M3, completely free upfront license fees. So we're trying to make sure that there's no barrier to innovation to people to put that in their designs. And we worked very hard to make that absolutely as approachable as we can. But what you get with that is not only commercial support, you get IP protection, and you get all the installed software base that works with that, which is very compelling value proposition. Because ultimately, if you're a company, you have to make a very simple trade-off of make versus buy. Now, Art and Esperanto, they made a make versus buy trade-off, but these guys are a big company. I mean, they have very, very audacious goals. If you're going to do a specialty application, you have to say, okay, do I want to take an off-the-shelf core that's proven, reliable, good to go, or do I want to do open source? Indeed, as Linley said, you may save some cost up front with the license fee, depending on which core you choose. But actually, there's a lot of make you have to do along the way, and you take in a lot of risk. And so for most of our partners, we really work hard to make sure that when you look at the total cost of ownership of the core plus the royalties, but the value of the ecosystem you get, that it's just a no-brainer that you're getting a lot more value to take our core.
So John, you talked about making at least some of the cores license fee free, but I think what Krste was talking about is also free to innovate, right?
Sure.
Free to add instructions. So I think that's something that Art, you guys are doing. So can you talk a little bit about kind of why you want to create new instructions? What's the value of that?
Well, so some of you may be familiar with a concept called an architecture license that ARM and MIPS and other people provide to some of their customers, which allows their biggest and best customers, the Qualcomms of the world, to actually modify the architecture, to invent their own microarchitectures, to make changes, do extensions, and so on.
I should just correct you. They modify the microarchitecture. They agree. So they're just going to give a quick micro lesson. There's two ways you can take an ARM core. There's what's called an implementation core, which is complete RTL ready to go. You plop it in your design and it's ready to go. Some licensees take an architecture license, which is you agree to comply with the architecture, but how you implement that is up to you. And then computer architects can then provide their own innovations.
And I had the pleasure of negotiating the very first ARM architecture license back at Digital, which became Strong ARM. Now, in our case, though, picture this. John and I are fairly close friends. So 3 years ago, if I had approached John and said, listen, John, we got 5 guys, we got Dave Ditzel, we got a couple $1,000,000, and we want an ARM architecture license, and we also want to license 3 of your cores. We want to license your highest end core, we want a mid-range and a low-end core for housekeeping and the like.
And you want to be able to modify the
And we want to be able to
instruction
modify it, we want to be able to extend the instruction set, and guess what? We also want to be able to sublicense. Now, John's green tea would have come out with his laughter, and he would have been just busting up, and he'd say, Art, are you crazy? There's absolutely no way. It's not a matter of economics. There's no way we will do this. Because if you totaled all up what I just asked for, John would have said to me, Art, that's like $50 million probably. I'm just guessing, whatever it is, pure hypothetical. But it was way more money than 3 guys in a garage could afford. So the idea of being able to innovate on an open source platform like RISC-V and do all those things that I talked about and leverage the open source cores that are out there, wow, what a fantastic starting point. And we have actually leveraged in our work some of the work from Krste's team at Berkeley. So it's a beautiful model, and it really does encourage innovation. And I don't mean to pick on John, we're close friends, so I feel like I can at least twist the knife a little.
But Art, for the people who may not be familiar with CPU design, what is the benefit of adding new instructions?
Well,
why is that so important?
In specialized applications, as John points out, there may be cases where adding instructions actually improves efficiency. There's some cases in point. For instance, adding crypto instructions to accelerate cryptographic functions can offer big benefit. That's a very simple one.
Is this like a small improvement or a big improvement?
It can be quite large depending on the application. Vector instructions, Krste is very active in the vector instruction set definition for RISC-V, another area of big improvement. And I'm sure, Krste, you could quantify that better than I can.
Yeah, I think it's well known, people have done many studies, you can easily get 100x improvement if you have the right instruction for a given task. And that's much bigger than any incremental 5-10% you get in scalar general purpose performance over the last bunch of years, right? So that's where, now it doesn't work for everything, but where it does work, it can work very, very well. And that's one of the reasons people build a new chip. Like, why don't you just take the existing chip and program it in software? Well, because I have an idea for a new widget that's going to give me that 100x or whatever. And that's why you go build a new chip instead of just programming one of the old ones. So when we designed RISC-V, like I said, it came out of a project looking at specialized processors. One of our goals in the architecture, there's some misconception that because you allow customization, you're going to cause fragmentation and your software won't work. Well, that's not true. The way we designed the ISA was, this is the standard stuff, don't mess with that. This is your playground, go do what you want. All the standard software runs over here. Provided you don't mess that up, all the standard software works. And what you find is that when you add the specialization, there's just a tiny fraction of all the lines of code you probably need to run that uses those instructions. So it's okay to have your playground over here. You still get to use the entire software ecosystem on your standard compliant core on this side. So you get the benefit of all that standard software and compliance and all that goodness. But you also get the playground over here where it's like a mullet, right? Party in front, whatever it is, party in back. You get to do both,
Business in the
right?
front, party
Yeah.
in the back.
There you go, yeah. I'm from the UK, I know, it's the US thing. So. Right.
So John, my understanding is ARM doesn't permit customers to modify the instruction set to ensure that all of the software will run on every ARM processor. Is that?
Yeah, that's right. And that's been crucial to the success of our architecture, which is really to the benefit of all of our licensees, because they know that the investment they get, they put in their product today is going to reap rewards in the future. But that doesn't mean to say we don't promote innovation and openness, because we do. At every level. So first thing, from a software perspective, we're very, very supportive of open source. I don't want anyone to leave with a misimpression that we're not supportive of open source. From an open source software perspective, ARM is one of the top contributors to the Linux kernel, where we sort of go between number 3 and number 4 via a group called Linaro, which is a joint venture between ARM and many of our licensees that we founded some years ago. And continues to be very active today. So we're very, very active in that. We have a huge set of people that are involved in that. Similarly, from a research perspective, we're extremely involved in academia and research. We promote access to academics to use our cores for their research and so on. So from an innovation perspective, we're fundamentally committed to providing that. From a specific extensibility on this specific question, there are many different interfaces by which you can extend ARM cores. There's existing ones, the existing lower speed buses, and there's higher speed buses we've announced recently a year or so ago called Dynamic, and there's even other industry consortia called C6, which is a collaboration with Xilinx and others. So there's plenty of opportunities to put accelerators on the side when you've got a special purpose application that you really want to accelerate that can work hand in hand with the architecture that we have that's fundamentally stable. I mean, I think when Krste says they have this instruction set carved off in this part and that part, I mean, that's literally true. The problem is when you get into actually implementing the core, it's not quite as simple as that to verify that one of these things hasn't caused problems in the other. And that's why we find it's too dangerous to be able to ensure that our licensees are going to have a compatible experience. And we provide these other means to provide extensibility.
Mm-hmm. So, Kaushik, so what kinds of end markets do you see some of the RISC-V companies that you're investing in or maybe that you've talked to? What kind of end markets do you see them targeting?
Yeah, so I mean, we have invested in both SiFive and Esperanto, and we'll do more. Talking about end markets, initially we're seeing the low end of the market, the IoTs, the edge, the video analytics, and things like that. That's the initial, I think, use cases. But then also, we believe that it will move up market as well. About a year back, we were talking to many startups building SoCs or controllers, microcontrollers, and about a year back, they were saying, we were asking, are you open to using RISC-V? And their response was, the tools are not there, it's not mature, we don't know. They were skeptical and nervous. Today, the situation is absolutely different. They are very willing to adopt RISC-V. It's there, it's ready, and the startups are embracing it. And I think it's the smaller, nimble startups, they are the ones who will embrace it before the large incumbents will.
Right, right. And in terms of Western Digital, I mean, can you talk to how Western Digital plans to use RISC-V?
Yeah, so if you think about what Western Digital sells today, it's hard disk drives and solid-state drives. Those are storage devices, and inside that solid-state drive is a flash or NAND memory, which is a commodity. But the real brain is a controller, both for the controller that controls the commodity NAND, or in a hard disk drive, it's the controller that controls the spinning platter or the ARM and reads the data from the spinning platter. So the brain is actually the controller. Now, we buy those controllers from Marvell and Broadcom today, and they use ARM cores for those controllers. Now, what we have said is that we will bring that controller technology in-house, and for those controllers, we'll use RISC-V. So our use case primarily is in building those controllers for solid-state drives and hard disk drives, which are basically the brains of the solid-state drives and the hard disk drives that we sell.
Right, right. What about all the flash memory, kind of the sticks and things?
Yeah, those are also a type of device which also uses controllers. And if you look at the USB stick, that also has a controller, and for that also we'll bring the technology in-house, and then we plan to use RISC-V for those as well. Mm-hmm. It's the same controller. I mean, the controller for a high-end solid-state drive are slightly more complicated, and there are controllers for the low-end USB stick that you can buy from Best Buy. But then again, the technology is similar. The brain is the controller, and we plan on using RISC-V for those controllers.
And when you look across all of those flash drives, hard drives, solid-state drives, you get into this billion unit kind of number.
Correct, correct. I mean, what our CTO has said publicly that we're gonna use it for billions. We're gonna use billions of cores for our controllers.
Right, right. So good, yeah. So I think how quickly can the open source community kind of build on the existing cores and the existing tools and improve the quality? I mean, you mentioned the superscalar core needs some work. I mean, you know, realistically, how quickly can that happen?
Yeah, I mean,
It is happening today, and I think one of you mentioned Linaro, which is the software consortium for ARM, and we think the software piece is coming there as well. Similar to Linaro, there's another startup called OSF, or Open Source Foundries. Those are actually founded by ex-Linaro guys. They're working on the software piece as well. But again, to answer your question, the adoption is there today. I mean, we are seeing startups starting to adopt RISC-V today, with or without the software. I mean, the tools are ready. The software is, I mean, I've seen demos of Linux running on RISC-V processors. So it's ready today.
Mm-hmm. Krste, how do you see things evolving?
Yeah, I think one thing to get clear, I think this might be confusing, is RISC-V is not an open source processor. RISC-V is a free and open specification. And that enables at least 3 kinds of delivery of processors. One is open source cores, like the ones we develop in Berkeley and other places. There's also proprietary supported, cores, like SiFive cores. The third category that's also very important, we haven't talked about yet, is build your own cores, where a lot of companies, what they like is the freedom of choice. They can source cores from any one of these communities. And in particular, at the government level, we haven't talked about why governments are interested in RISC-V. And this is precisely because they can build their own secure core that they trust without needing an architectural license. And more especially with RISC-V, it's a very simple ISA. So they don't need a huge amount of resources to build that core that they can trust and verify, formally verify, but still get access to the whole software ecosystem. So I think it's important for people to realize RISC-V is not only for open source processors, it's also for commercially supported, people stand behind you cores. It's also to allow you to build your own cores. And more importantly, you can choose where you get your cores from. And unlike before, it would be the model before was pick your vendor, then you get an ISA. Whereas RISC-V, you pick an ISA, then you get to choose a vendor or do it yourself. That's a fundamental switch in the business model.
Mm-hmm. And then do it yourself is what Esperanto is doing, right, Art?
Yeah, exactly right. But leveraging the starting points that are out there and then adding the features and changing the architecture as we need to.
Mm-hmm. So kind of a hybrid model that you can take the open source, start with that, but then add your own customization on top of that.
And have effectively no limits to what you do.
Right. So I guess, John, what about companies that want to create these custom instructions? Is there any way for ARM to support that?
As I said, our focus has been on providing, first thing, by providing a range of processors from extremely low power up to extremely high performance, including those that have things like vector extensions, multimedia extensions, crypto extensions, virtualization in our most recent processors. There's quite a lot to like. And I also should say that it's a misconception that we have like a smoke-filled room where our architects come up with this stuff. The reality is we have what's called an architecture review board where we work with our architecture licensees and our major customers to say, where's the trends going? What are the innovations that are coming down to ensure that we put them in our architecture in a way that's accessible to all. Then you couple that with, as I said, high-performance interfaces so people can put high-performance, low-latency accelerators close to the chip. you get the opportunity to get kind of the best of both worlds with a lot of stability.
So you can actually work with your customers and they can help define.
We do, and our architecture licensees are extremely involved in that, and
maybe like with the scalable vector extension.
For sure, and we're looking at, we just announced those like last year and perhaps the year before that, the latest extension of that, which allows the next level of the work we did previously with Neon, which was our the equivalent of what Intel MMX.
I believe Fujitsu was very helpful with the scalable vector extensions.
I don't know exactly which customers, but the fact is this review board for us is something that happens very religiously, and we're very committed to making sure that the partner feedback goes right into our architecture for the future. And the thing is, you have to understand, especially at the high end, the kind of man years it takes to make a new processor is substantial. So when you couple that with the verification of the processor, the resources it takes are colossal. I mean, Esperanto is well capitalized to get their work done. So I think the ultimate point to take away from this is the idea, as Linley's chart showed, if you saw earlier, the idea that a free processor, if that's what draws you to it, free is not free. Robert Heinlein once coined the phrase, "There's no such thing as a free lunch." And the reality is, when you get a free processor, the problem is you got to do a lot of work to buy that freedom. And for some people, that may be the right trade-off. Certainly for research, we see that this is a great platform, and if I was a researcher, I would be using this all day long for computer architecture research. But as you get into commercialization, there's some concerns.
Now, Art, there are other companies that offer instruction sets that allow or even encourage you to make modifications. I mean, Extensa is pretty much founded on that principle. Did you guys look at some of those architectures as well as ARM? And
really, given our focus at that time was to develop our own, we looked at ARM in great detail, and then we looked for alternatives.
Right.
But the most obvious alternative for us was indeed RISC-V. And part of it was just the whole business model, the free and open standard, and the fact that even 3 years ago, you could see the beginnings of the momentum. I mean, if you look at an open source initiative or an open standard initiative, this one's fairly amazing. And if you contrast it with other attempts to open source processors in the past that were total failures, you can really see the difference. I mentioned that I had the opportunity to launch the Sun UltraSpark processor earlier in my career. And that was in the 90s when Sun was the go-go company of the Valley, and the network was the computer, and we were the dot and .com and all that good stuff. But the processor that was driving all that was UltraSpark. That completely changed Sun's fortunes from being almost a dead company to a great success in that era. Well, a few years later, Sun decided to open source that processor with the so-called OpenSpark initiative. And it was a complete and total dud, because it was obvious to everyone involved that what Sun really wanted to do was put some lip service out there that they support open source and encourage innovation, but really they wanted to sell proprietary hardware and software. And so the community never developed. And if you contrast that with what you see in RISC-V, where you have not only academics, but students and researchers and developers and big companies and small companies and more joining all the time, it's completely different than those other past open source efforts. And I don't think I've seen anything like it since I ran a Linux company in the early thousands, and that's how hot Linux was at that time. So for me, this was the only choice.
so we will be able to take some questions from the audience shortly. I want to ask one more question before we do that. I think Kaushik's probably the best guy to start on this. So, RISC-V, as we've been discussing, is a very innovative technology, but how do you see companies being able to make money off of something that's freely available? What kind of business models do you see that will kind of work with this open source concept?
Yeah, so at this point, it's unclear to us which business model will eventually, get the most traction. For example, if you look at SiFive, they're full service. You want a core, you want an SoC, you want a chip, they'll ship you whatever you want. That's full service. On the other hand, there are companies that are just doing providing the IP. So at this point, it's unclear to us which business model will eventually get the most traction. So we'll be supportive of both the models at this point.
Okay. Krste, with SiFive, as Kaushik said, kind of the full service model. So, I mean, as a company that is basically selling design services, I mean, who do you see your competitors being?
Sorry, say that again?
I was talking to Krste, sorry.
Okay.
Yeah. Well, I wouldn't call us a design services company. We're a custom ASIC company. So when we started the company, like when we started up, like, okay, it doesn't make any sense to be a core IP company. Who would do that? We have a free and open spec. We did some pretty good open source cores at Berkeley. How would you ever make money selling core IP? That was our thought when we started the company. And we focused on the chip side, which is what we have been developing, cutting the cost of doing chips. But within the first few months, all these companies, we had no luxury of being a stealth startup. Everybody was excited. They want to know what we're doing. So we had a huge stream of companies come to us saying, can you give us a RISC-V core? And the first few weeks, we were like, or first few months, we were like, we don't do that. Just take the open one. Like, go away, leave us alone. We're busy doing this other business, right? And then after like 10 or 12 companies come by, and you're like, wait a minute, we're a startup. We need some money. We have a product that people want, except we didn't realize quite what people wanted. It took us a little time to tool up and actually deliver commercially verified cores that met their needs. That was a bit of a sidestep for us. So that's definitely one business we have. Like I said, we did not anticipate that being a part of our company when we started. But like any startup, you adapt to what the customers want, and that's what they wanted. But our goal is to make money from selling chips. So for us, the core is not the centerpiece of what we do. Is we want to get customers to silicon, build custom silicon solutions. That's what we are trying to enable. And we want to be this platform in the middle where I think what we also see is a lot of people who come to us wanting to build a chip. They haven't realized that they really are actually an IP company. They have a widget, and their only go-to-market idea is build a chip. What they should be doing is coming in with their IP, and then they have a much bigger customer base. So people want to take that IP, mix it with this other piece, build a different chip, and that's really the model. So our goal is to be the guys in the middle who are helping everybody get to market. Like if you're an IP provider, you have somebody an idea for a product who needs this IP, we want to be that go-between in the middle that provides that platform for everybody.
And then Art, I think, Esperanto sort of embodies this business model of being a chip vendor who just happens to be using RISC-V, and I've seen plenty of others. I listed a few on my slide. Would you say RISC-V is just an ingredient that helps chip companies become more successful?
Yeah, and provides an opportunity for that innovation that many of us are looking for. And not to make too fine a point of it about the process of the architecture committee at ARM and so on, but if you think about the process that John described, and those big companies with their big infrastructure, it might take a long time to get a new feature implemented into, from the ARM architecture committee through that group, the big companies agreeing, and then it's showing up on a roadmap. And the difference is with this kind of platform, you can make those innovations sooner. Now you do take risk. You clearly take risk in doing that, but you're depending on the ISA itself to have a good verification suite and to make sure that you're in compliance and so on. So it's a trade-off. You get to innovate, but you take slightly more risk.
Mm-hmm. Okay, great.
There's just one I'll take on that last.
Oh yeah,
that
sure.
last
Sorry,
question.
go ahead.
No problem. No, it's fine. I think what SiFive has done. Let me praise them for a moment. And what they've done is they've taken advantage of the cloud environment and some of the trends that are going there to be able to provide an alternative model to making a chip. And I don't quibble with that at all, no doubt. I mean, there are a host of companies that exist today that have ARM IP on the shelf now, have experience in developing ARM IP, and if you, as Krste wisely said, if you have an innovation, a widget you want to plug into a chip, there are companies today that exist, that have been in the business for 20 years, that can put that into silicon for you. Now they've got a clever business model how to do that, but the fact is that exists today and you can achieve. And I think what Art said is probably literally true in terms of new features that come. But that's why we're providing access to innovation at the system level and other ways to get that IP into there, even if it's not right under the covers of the core processor itself. I think we try and get the best of both worlds.
Right. All right, great. Thanks, John. So we do have some questions from the audience. If you have questions, you can text them to the number that's on the screen, and they will apparently show up on my iPad. So technology works. Just to start off with a question from the audience, I might as well start with the elephant in the room. Is RISC-V an existential threat to ARM? I think, John, you should probably address that first.
I mean, we see RISC-V as a natural step in innovation, and it's praiseworthy. We have a lot of customers that depend on our architecture every day, and we talk to them, and they like what we have and want to buy more of it in the future.
Mm-hmm. So, and there's a software base.
There's an incredible software base. There's an incredible design ecosystem. It's over 1,200 companies that basically their living is either inextricably linked with ARM or largely linked to ARM. And they've got a lot of inertia around the work they've done with us. The number of companies that are already licensees of ARM, which is over 500 companies, maybe notwithstanding some industry consolidation, the amount of investment that people have put into that is huge. And we see companies wanting to leverage that investment, and we want to make sure that they can be happy to work with us for years into the future.
And
can you put up the number for extra questions?
The number was on the screen, and now it's not. Okay, there we go.
Can I make a comment about that existential threat?
Please.
So I would say today, obviously not. Okay? But one thing I've learned over time is you have to pick your battles in the processor wars. Are there any fans of an old movie called The Princess Bride in the audience?
Of course.
Okay, yes. So there's a famous character in that movie, a Sicilian assassin called Vicini, and he makes a comment that one of the fundamental mistakes you can make is to launch a land war in Asia. Now, the equivalent of doing that in the processor world is to attack an entrenched monopoly or quasi-monopoly in their strongest segments. You'll get killed. And I mean, I personally have followed that path. I took MIPS head-to-head against ARM in mobile processors, and we got annihilated. Not from any bad practices on ARM's part, it's just they had a tremendous ecosystem that they could bring to bear, and we were developing that ecosystem. So I would say in the case of RISC-V, it's going to be quite a while before we could rival ARM's ecosystem in those key fundamental segments. Now, in other segments, the ecosystem requirements are much less. So for instance, in machine learning, that whole ecosystem is developing as we speak. And no architecture has a particular advantage over any other except for perhaps NVIDIA, because they're the entrenched competitor today. So in that case, really that ecosystem has no particular advantage today, or arguably, versus ARM. Now, John and I also went head-to-head against Intel at Transmeta. And another strategy is to pick a small niche where the other guy doesn't have a SKU that fits. So in some ways, that's kind of like what Krste is doing. It's a business model attack, or I shouldn't use the word attack, but a business model that's quite different than theirs. Mm-hmm. And so there's an opportunity for real differentiation and real traction. But you have to pick your battles and pick your niches, and I think anyone who wanted to try to displace ARM in mobile today would have a very difficult challenge.
I think it's inconceivable.
Well done.
Perfect.
Well done. Well done, Linley. Well done.
Krste, where do you see ARM in 10 years?
I look forward to ARM's RISC-V cores, actually. Because I look forward to ARM's RISC-V cores. They're a wonderful company. They build great products. Build a great ecosystem. I used to have on my slide, if ARM meets your needs, and you can, if you want to use them, you should go use them. You'd be crazy not to use them. I used to say sometimes they don't meet your needs, and some people are just crazy, right? So that's why they use RISC-V. So it's great products, and I look forward to ARM producing RISC-V cores because I think they're a very capable company at building this stuff. It's very easy, as we see in many of the second-tier ISA providers, to move from their own ISA to RISC-V. And as more people demand RISC-V as a standard, I think there'll be a demand there, and they're sound business people at ARM. These are very sensible people. I think you'll see Risc-V cores from ARM as well. So that's my prediction. I don't think ARM's going to go anywhere. They're out of business. We never created Risc-V. I mean, people like to, in the press, like to do the David Goliath thing. That was never our intent. We just had a need. Risc-V filled our need. We're glad that other people find it useful too. And like SiFive is a very different business model. We're not, in fact, we view ARM as a partner in SiFive, right? We want to build chips. We want to help as many people build chips as possible.
And I'll say, as an academic, I think or as a former academic, the innovation and the focus around computer architecture innovation that has been coming from the discussion of Risc-V is very healthy. We go to the Risc-V workshop because we want to see all the interesting ideas that are coming up there, and we want to make sure that we're leaving no stone unturned to make our architecture as good as it can be. So I think that's a fantastic platform for research, for sure.
Yeah, I also want to give a shout out to Intel, who are by far the biggest industrial sponsor of Risc-V. And one of the reasons they like it in education, just to echo this point, is we need more students who understand computer architecture deeply and not just play with simulators, play with real cores. Unfortunately, over the last 20, 30, maybe 20 years, a lot of architecture research is focused on like C-based simulators. People don't build enough chips, enough hardware. And now we're at the point where, you know what, we need a lot more computer architects than we did a few years ago. And we need that talent base. So, we produce this in education because I like building chips. And we need more students who understand how to really build things. And this benefits the whole ecosystem, whichever I say you pick. But just the hardware industry in general needs more skilled architects. I just returned from China, amazing place in terms of opportunity, Risc-V and other places, but a distinct lack of talent. They really do not, there's a sweeping statement, they have very thin coverage of architecture. I think one thing I like to say, I feel like ARM has lobotomized large parts of the ecosystem from doing processor design because you could just get it from ARM and it works, right? Why would you do it yourself? You can get a great functioning thing, but building up that education, that knowledge, because we are going to need a lot more architecture, a lot more hardware, because scaling stopped, and so that's where we need innovation.
Okay, so let's move on to some other questions. Question, who pays the ecosystem to develop the software that sits on top of these open source processors?
So I'll take this. So one example I like is the Fedora guys. So they're not members of the foundation, they're just interested people, and they ported a lot of stuff to Risc-V. And Debian did a distribution. I hear rumors about how much other companies had to pay them to do their ports. And then magically, these ports just appeared from nowhere. In fact, my students were sending email to Debian saying, can you port this package? They go have lunch. After lunch, the package would be ported. So it's a wonderful open source community out there that really, I think they like the Risc-V idea, and they've been doing that. They've been doing a lot of development. Now, that will never be enough. I think the example ARM had of they had to put all this money into Linley. There's all the fun stuff in open source. Then there's the other stuff that isn't fun but needs to get done. And
bootloaders, drivers.
Well, some people think bootloaders are fun for some reason. But there's definitely these corners that need to get driven out with real money and real investment. But if you look at the Risc-V Foundation right now, we have over 110 companies, including most of the biggest companies. They have resources, and they are motivated to support filling out these corners. And as people forget, most open source projects, mostly it's donated by large companies, like ARM is a big mover in the open source community, Intel, others. They donate a lot of time and effort to the open source software community. And most of that open source software is portable to Risc-V. It's not like it was written to be X specific. It's very portable. That's why we've managed to come along so fast. It's leveraging all that earlier investment in open source software.
And Linley, if I just might make a point, in past lives, I might have had a $10 million porting budget at other companies where I've worked to go pay people to do ports as necessary. I don't see any need for it today. The ecosystem is developing rapidly. The tools vendors are there. It's almost like people think that, hey, this is so exciting. I want to be part of it. I have students coming up to me all the time saying, how can I get involved in this? My school is not yet teaching Risc-V. How do I get involved? And I said, it's open source. You feel free, jump in. You can engage.
From Esperanto's standpoint, though, I imagine there's a lot of very specific software, firmware that you would have to create.
Yes, absolutely.
So that's still in your budget.
Yeah, but I mean, spending outside. This was a
Sure.
third-party budget where you needed to incentivize a tool vendor or a library vendor or an OS vendor to do a port for you.
To a proprietary
Yeah.
architecture.
And I don't think that's necessary anymore
No,
in the
not if you
RISC-V
use
world.
RISC-V, yeah.
I mean, just on the point of academics for a sec, while I did make the point about computer architecture research, we've had a very, very active program in research universities around the world, making sure that we're exposing ARM cores and related computer architecture topics. We've got a very vibrant program to make sure that we're enabling the next wave of architects as well. And I hope that we can be a big part of that research.
So another question, I think along a similar line. The RISC-V has a compliance suite. How is that going? When is it going to be available?
Yes, we have an initial set of tests that are far from adequate, that are currently there. We have, at the foundation, we are funding commercial development of the real set of compliance suite tests. One thing to realize in RISC-V land, there's been a lot of effort on the formal side, formal models of the CPU, and some of those proposals are to drive that, to build a compliance suite in a formal way. So I think one thing about RISC-V is really engage a lot of academics to contribute. The one thing is being simple enough that people can apply some of these methodologies relatively straightforwardly. So I think you'll see in the next few months, you'll see the compliance suite advance a lot. In practice, it hasn't actually been an issue. It's one thing that you could imagine would be an issue. But for example, there are, I think, currently 4 different formal models of the RISC-V ISA. Those 4 models have all been checked against each other. So in practice, people know what the spec is, and there are 4 formal machine-readable versions of the spec. The reason there are 4 is some of them are used for you want different projections of the formal spec for different tasks. But there are 4 that are formally matched. We're going to be releasing one of those as the official golden model. It'll be a formal machine-readable model of the spec. So in terms of checking compliance, if you have a more capable CPU team, you can actually do that equivalence checking to make sure you're compliant. The compliance suite will also be useful. One of the goals is, one of the models of the foundation is we always release the spec, the golden model, and the compliance suites publicly to anybody, not just foundation members. And that's part of the charter. And we're actively funding development of this next compliance suite.
And then, John, the question is, ARM states they have a robust compliance, but their architecture is fractured. How are you dealing with that?
Fractured in which way? Well, so I think the questioner is asking about the 3 different architecture families, M, R, and A, have compatible but not exactly the same instruction set. So within the M family, within the R family, within the A family, those are common instruction sets, or rather I should say supersets. So you had the ARM v6 instruction set, the v7 is a superset, v8 is a superset of that. So it's backwards compatible. There is large compatibility between the 3 so that if you have learning within your organization about how to use that transfers across architectures, but the software is not directly 100% compatible. I think that's the question.
And there's the ARC32, ARC64.
But again, that's a backward compatibility thing. So for the longest time, it was 32 bits. About 7 years ago, 5, 6, 7 years ago, we rolled out our 64-bit cores. Those cores are run in either 32-bit only mode, 64-bit only mode, or a compatibility mode between, and that's again, backwards compatible.
And so your compliance suite, does it comprehend the difference?
It comprehends the whole range of that. And I mean, our architects, these guys are amazing, a team of architects. They work incredibly, and if you look at our high-end cores, now this doesn't apply to low-end cores, our high-end core, the architecture reference manual, which by the way is publicly available, you can read, is 6,000 pages. And that's because that's the complexity of these high-end cores. If you want to deliver these sort of Xeon class cores that we're now rolling out, you have to have that level of capability if you want to get into these high-end applications that we're targeting. So it's a non-trivial investment that we bring to bear on that. Of course, our low-end cores are much simpler, much more streamlined, that you can implement more straightforwardly. And those, of course, suites are comparably simpler.
Okay, we have a question for Kaushik. What is your time horizon for return on investment in the RISC-V ecosystem?
So we are strategic investors, so we're not measured by ROIs all the time. But yeah, we do want to make money. But the fact that we have been able to, or we are participating in seeding the ecosystem. That's a good return for us. And eventually, in the next 5 years or so, if we can bring our controller technology in-house, we'll be saving lots of money. I cannot really quantify it at this point, but yes, we spend huge amount of money on those controllers. So if we can build those in-house, that'll be a lot of savings for us.
Okay. And I don't know, Art, do you have any comment on the time horizon for your investment?
Well, I think if I have to say, there's insatiable demand for energy efficient AI solutions for machine learning in data centers and at the edge. And it looks to me like it could be a very fast revenue ramp for those companies that get out there first and establish a position. Part of the reason we're using RISC-V, though, is we believe that the algorithms involved are going to evolve rapidly. And so we chose to have a general purpose processor architecture such that we could evolve with those algorithms. But I see it as pretty explosive growth potential in that market.
Mm-hmm. And has RISC-V helped you get to market sooner?
I would say definitely.
Yeah. So reduced time to revenue. So question for Krste. We've heard about some of the side channel attacks, Spectre, Meltdown, that affect the Intel CPUs, some of the ARM CPUs, a lot of other CPUs. How is RISC-V dealing with that?
Yeah, so the thing to understand is most of those attacks are not specific to an ISA. They are attacks on a particular microarchitectural style. So if you provide, if your processor does any form of advanced speculation that leaves a trace in the microarchitectural state, that can potentially be exploited by one of these attacks. That's why those attacks were common to Intel and AMD and ARM and Power. And fortunately, RISC-V, the cores that were out there commercially were simple enough that they weren't susceptible to that. But for example, the boom out of order core, the academic core we had, that would have been susceptible to those attacks. It just wasn't a commercially supported core. Now, the thing with RISC-V and security in general, there's been a huge adoption of RISC-V in the security research community because it is open and accessible. And so we're hoping it's a great breeding ground for finding solutions to a lot of these security challenges. One big advantage RISC-V has, apart from being open, that is one big advantage by itself. Second big advantage is it's simple. And so there's a lot of work at Berkeley and other places on formally verifying security properties of microarchitectures, things that would tell you that you are susceptible to, for example, one of these styles of attacks. Some other signs are, for example, DARPA has the latest security research program. They actually mandated the use of RISC-V in that program. And we see this with government-level agencies around the world are fixating on RISC-V as a security solution. Also, there are a lot of companies providing RISC-V secure cores. And again, I think it's a combination of simplicity and openness is driving the use of RISC-V for security.
So when you say the RISC-V cores are open, so it's easy for a government to say there aren't any security flaws. Is that?
Well, there's a couple of aspects to open. One is that because it's open, you can build your own core that you trust.
Mm-hmm.
I don't know if any governments have architectural licenses. The second one is that you can, if somebody gives you a core, you can, if they give you an open core, you can inspect the code they gave you. That's the second aspect of being open. I think simplicity is another benefit, a big benefit in this space.
But you're saying if a government wants to have a secure core, they would use the instruction set, but then they would design their own microarchitecture, not expose the architecture.
That's right. And also, they are free to add their own, as these many research groups are doing, they're experimenting with new security mechanisms. And it's very easy to go just build the core and try these ideas out. For example, in the DARPA program, they are putting these machines out on FPGAs and expose them to red team. So here you go, here's my security idea, go attack it, right? So they can build a prototype, put it out there, And this is why it's being used in research in this space. So I wouldn't claim that RISC-V has solved security, by no means. This is going to be continual arms race for the next 100 years or whatever. But it's a platform to do development.
But could I make one additional comment that you didn't comment on, Krste? So the collaborative nature of RISC-V also comes to bear. So Esperanto does use speculative execution on one of our processor cores. And so two of our employees, actually one of Krste's former grad students, Krste, who is the designer of the Boom, architect of the Boom core at Berkeley, and Professor Jose Renaud of UC Santa Cruz, actually have presented papers on different mitigation techniques that we could apply, and invited the industry to comment and trying to bring in discussion, and there's working groups who are collaborating on it. Again, this idea that with more eyes, all bugs are shallow. I know it's a kind of a trite expression, but when you see the collaboration actually happening, it makes me believe it's true.
Mm-hmm.
Okay, so I'll add a couple of points. There's, where do I start here? First is talking about the side channel attacks. The vast majority of ARM's processors were not affected by the side channel attacks. There was a small fraction that were. And the fact that we have such an open model with our partners allowed us to work very collaboratively with them to make sure they could mitigate those quickly. So that's first. Second, talking to the point about open specifications, so you can know there's no backdoors and so on. While our IP is not readily available to everyone to read, our licensees get the full source to our IP. So they have full transparency to see what's in there. They can reassure themselves that they're confident of that. And that's the case even with, in many cases, research projects or government projects in some cases that have used that. That was the third point you just made about...
collaboration?
Yeah, collaboration. I lost my third point.
So, John, when the Spectre meltdown were discovered, the groups came to ARM, Intel, some other companies in advance to allow you guys time to develop countermeasures. Is that right?
Yeah, I don't think it's appropriate to go into the details of that, but yeah, the whole point of it is that the industry collaborated to make sure that we can provide mitigations to minimize the impact of this threat.
Right. So Krste, if you can imagine the RISC-V was in a situation where it was potentially affected by this kind of thing. I mean, how could an open source community respond? Right? Who would you notify? I mean, the point of notifying some of these companies was they were able to keep that under wraps while they developed countermeasures. How could an open source community respond in that kind of situation?
So at the foundation, we've created a security standing committee. It's led by Elena Hanshu from Rambus CRI, and vice chair is Joe Kinnery from Galwa Research. And so they are setting up a responsible disclosure process for RISC-V implementers. So one thing is, for responsible disclosure, you don't want to just announce the vulnerability to the whole world. You want to have a path for implementers to be notified. And so that's the mechanism of putting in place the foundation to handle responsible disclosure.
And sorry, Linley, you actually just reminded me of the third point I was going to make, that Art talked about the community coming together to find problems. And I think that there's a lot of truth to that. But I think it's also important to understand that openness is not a panacea. Because if you look at the SSL,
Sure.
for example, SSL has been around for God knows how long, and a few years back they found a
Poor
fundamental weakness.
implementations are always bad.
Yeah, they found a fundamental weakness in SSL. So I think it's, sunlight is helpful, but it also doesn't solve every problem. And that's why, at the end of the day, you want to make sure there's a commercial entity backing the thing that you're really betting your business on, because we wake up every day making sure that it
Yeah, I'll just respond though and say, commercial entities, if you look at some of the most trusted companies, have not managed to, everything is broken. So that's probably an understatement, but pretty much everything is broken. So nearly all the security mechanisms have been broken. So that's not actually a reflection of the companies as much, just to say that it's a really tough problem. And so a few exceptions of maybe things where the value is not high enough to warrant the attacks, but pretty much everything has been broken. Like the recent SGX, I don't know how much they invested in that system, but that's basically broken. And mostly of the security mechanisms those companies are selling are also broken. So the reality is nothing works, right? So we have to all work together to come up with something that will work better.
And with that, Krste gets the last word, and we're out of time. So I'd like to bring Dana back up to close the event.
Thank you, guys.